Hello everyone. So today we'll be discussing about one important topic, strain, and further we'll be discussing how to measure this strain using these strain gauges, and we'll be discussing about further about this. First of all, let's understand what is strain. Strain is kind of an obtain. It's a effect. So when someone applies a stress on the body gets deformed, like a rubber band. If you have a rubber band, it stretches on the application of load. So deformation is the measure of how much a body is stretched. Strain is directly related to the deformation, and its deformation gives you an info about how much a body is deformed, or stretched. As I said in the example of a rubber band, as I apply a load on the rubber band, the rubber band stretches, it deforms. So strain actually is the ratio of this amount of deformation by the original deformation that you have. That means, for example, if you have a typical rod, a typical bar or a rod of length L, and you apply a load P on this rod. So your strain, then due to the application of this load P, your body deforms at certain point. And this deformation, let's say, is known as delta. Then your strain will be your change in the length by the original length. So change in length is delta, and your original length is L. So strain is represented by epsilon, is delta by L. It's change in length to your original length of the body. So it gives you an information of the amount of deformation occurring inside the body. So further, it is also of two types. So one is a normal strain, and another one is shear strain. So strain usually, as you see there, this is the ratio of the length. Change in the length by original length is the ratio. So strain is dimensionless quantity. Though stress has a unit of MPa, Newton per meter square, but strain is a dimensionless quantity. So it's a dimensionless quantity, change in length by original length of the body. So let's define the strain in more of the kind of a coordinate system in which there will be different strain. As I said, there are normal strains and there are shear strains. So normal strains are acts on the body where the load is normal, and shearing effect is occurring due to the deformation of the body. So normal strains are along the axial directions, and shear strain is on the transverse when the load is transversely effectively. So let's discuss this in a more official way. Like if we have some kind of a particle and on the application of this load, this particle changes its length. So let's say the length of the particle is delta x, and after the application of the load, it gets deformed in delta ux, where u represents a deformation. Okay, u represents a deformation in particular direction, x. So your strain epsilon x will be change in length. What is change in length? Delta ux upon delta x. Change in length by original length of the body. This is epsilon x because we usually take the coordinate system in this form. So epsilon y will be delta uy. U is the deformation again, by delta y. So will be strain in the y direction. In a similar way, if there will be a z direction, so this will be delta uz by delta z. In a similar way, there occurs these are the examples of a normal strains. In case of a shear, something like if you have the element and it shears. So shearing occurs usually when you apply some kind of a moment or some kind of a non-axial forces to a body. So a shearing of the element may take place, and your element may shear or may deform like this, may deform like this, may be directly linear, may not be linear, that doesn't matter. But when it shortens, it gives you some orientation here, and here also it gives you some orientation theta. So this deformation is, let's say, delta uy, because it is along the y. This is the effect of deformation, change in length, and these are the delta x and delta y's, and this will be delta ux because the deformation is along the x. Correct? So your what will be your this deformation? If this is some kind of a linear, then this is tan theta 1. This will be delta uy by delta x, and similarly there will be another tan theta 2 will be delta ux by delta y. So your overall shear strain will be tan theta 1 and tan theta 2. Now in the case of normal strain, we represent the normal by epsilon. However, we represent the shear by gamma. Represent the normal by epsilon, we represent the shear by gamma. So this is something very simple, like normal stresses are represented by sigma and shear stresses are represented by tau. So the shear gamma xy will be the sum of these two shearing effect, tan theta 1, tan theta 2. So however, the sum will be delta uy by delta x plus delta ux by delta y. Now this can be further reiterated for yz and zx, both of them. So this comes in a similar fashion. The other equations will be there. For gamma yz will be delta uy by delta z plus delta uz by delta y. Similarly, gamma xz will be delta ux by delta z. Sorry, this is delta plus delta uz by delta x. Now, as you can see, these are the linear strains. These are the linear strains. These are the shear strains. So they give you a shearing effect and give you a normal effect or a linear strain along the axis. Now the important thing to advise here, these are the small deformation, delta ux, delta uy. Here also if you can see tan theta 1, tan theta 2, and definitely we have considered theta as to be very small. So there are two kinds of strain theories. Strain theory, and these strain theories are differentiated based on the deformation. So based on the deformation is small. We have a small strain theory, and the deformation is large. We have a finite strain theories. So in a small deformation theory, we consider the deformation to be very small. So these thetas are also very small. So that's why we have added here tan theta 1, tan theta 2. And also, as you can see, that the variation is occurring on the application of the strain, on the application of the load P. The variation is occurring along the x also and along the y also. So that means if you consider this as a small strain, you can put the delta as to be a derivative d, and since the variation occurring in 1, 2 and 3, all the three sides for a solid body, for a solid three-dimensional body, then this d can be replaced by del. So these equations here all replaces by del here, in the numerator also, in the denominator also. Correct? Here all can represent them by del. You can derive them also. There is a derivation of these are also possible. I am telling you in the most convenient way how they are to be related. Further, once you have put all of them together, so delta x will be del ux by del x. Delta y will be del uy by del y. Change in along the y by deformation delta y. So if you put a small strain theory, we'll be discussing majorly a small strain theory only here. The finite strain theories will be taught in the higher classes. This includes the deformation. Addition to the deformation, it includes the rotation also. So body gets deformed and gets rotated. So all these components of strain can be arranged in a tensor format, like we have done for the case of stress. So you can say that our matrix epsilon ij will be equal to epsilon xx, epsilon yy, epsilon zz. Correct? And we have here gamma xy, gamma xz, gamma yz, gamma yz. I'm taking the symmetric matrix xz, xy. Correct? This is a matrix for you. Now there is a small catch and small kind of substitution to this. When you use more kind of though we have considered the small strain theory, but we have considered the small strain theory only because the theta is very small. That means the shearing angles and the effect of non-linear terms are almost negligible. But in the finite strain theory, the non-linear effect terms does include, and the deformation is huge. But we have to ensure that the theory remains consistent. That means whatever is applicable to the small strain theory will be linearized and will be further continued for the finite strain theory. The story that is left here will be continued in the finite strain theory. So if you go to the finite strain theory, the stress tensor is somewhat different. Different in the sense that the shear here, gamma xy by 2 occurs. In this also, in all the shear terms, there exists gamma xy by 2, and there exists a special vector epsilon xy, like example, is equal to 1 by 2 gamma xy. This is a tensorial strain and this is a engineering strain. So gamma xy here is a engineering strain and epsilon xy is tensorial strain. And the effect of this half, or 2, you can put here as 2 epsilon xy. So the effect of this half will be known to you more when you will be considering the finite strain theories. Just here, let me be with you that there exists a epsilon xy is equal to half of gamma xy. So these are only the terms the way. As you can see, this is epsilon xy is a tensorial strain. Tensorial strain. And you why this, and this is engineering strain. So as you can see this tensor, the effect of 1 by 2 is because of the way the tensor behaves. So in the equation, the tensor includes 2 epsilon xy as an equation corresponding to gamma xy. That's why, in fact, in all the shear terms. So that's why the effect of half is there. So this will be more clear as you reach to the higher classes. So, but the strain tensor is like this kind of. And here is very important to mention that all the concept of principal values and principal directions will be applied here also. I mean, there was a stress tensor which has a principal values. We call that as a principal stresses, and we call them the corresponding directions as principal directions. So the case here also is same. The matrix is same. All the properties, the matrix is also symmetric. It also has principal values. So there is something called as principal strains also, and there is something called as principal directions also. Get me? There are principal strains also and principal directions also. So when we apply a load on the body, load like stress, the deformation occurs, and these deformations are these strain. So there exist a principal values also, principal direction. There will be a principal value along which a principal direction exists, and along this direction the maximum deformation will happen. This is what the principal direction or the principal strain value means, and there will be a corresponding minimum value also. The two planes will be there, maximum value and minimum value, and they will be separated by 90 degrees. You know that. So as we now know that there exist all these concept of stresses will be applied here also. The important thing, the important question that is that arises in mind that the stress strain has same principal directions. This is a very important question. Are the stresses and strain have the same principal directions? Let's say I have a body and I have oriented that body to a particular plane, and let's say that plane is a principal plane. So there exist a principal stresses. So the point is, are on the same plane exist a principal strains also? Are on the same planes exist a principal strains also? That means the plane has the same plane will be having, or this same question can be reiterated in another way, that are the principal stress and principal strain has same plane. That means they have the same maximum principal plane and minimum principal plane. Well, that's a very, very important question. If you get the answer of this question, really that gives you a whole of the bundle why the stresses and strains are there, and how they are connected together. There is a connection between the stress and the strain also. So we know that there exists a sigma and there exists a strain, and the connection between the stress and strain is the stiffness of the structure. That means you deform the body. You deform the body, but how much the body deforms? The aluminum may be deforming more. The steel may not be deforming that much. So there is a difference in the deformation, and the deformation difference by application of the same load will come as an effect of different stiffnesses of the structure. So a structure has a stiffness of its own, and we used to call that stiffness is usually 1 by E. We used to call this as a modulus or principal proportionality constant also, or slope of the curve also. So we'll talk about this modulus later, but what I wanted to say is that the let's say I have a body, and that body has three axes, along the x, along the y, and along the z directions. So I'm trying to answer this question. If the properties like this modulus or strength of the body along the x, along the y, and along the z directions are same, such type of body is called as isotropic body. Isotropic body. This is a body in which the properties are same properties exist in all directions. Same properties exist in all directions. If the properties are same in all the directions, then your planes of stresses and strains will be same. If the properties are not same in all the directions, then the planes of stress, the principal plane of stresses and principal plane of strains will be different. That will depend upon the property along which the direction, because the stiffness will be different. As I say, stiffness or modulus, whatever you call this, it will be different. So the stiffness, if stiffness is different, then the stiffness basically depends along the particular direction of the body. If stiffness along the x direction is different in some materials, and stiffness along the y direction, let's say that in wood, the properties are same in two directions, but the property is different in the third direction. The properties are same in the two directions. In the plane, the properties are same, but in the third direction, along the length of the oak, the properties are different. So the principal planes in the third direction, in that case, will be different. So for principal directions to be same for the stresses and strain, the properties must be same. And we'll talk more about the modulus and how it is related, three-dimensional modulus, more about this in some other video, not now. We'll be discussing, we would like to continue our discussion of strain. So since we know that now, that this is a strain matrix, and the principal operations of principal values of principal direction in a similar way can be operated on this. Now I would like to more discuss on how the strain should be measured. We know that the stress can be measured directly, is the applied load, but how to measure strain measurement? And further, there is a need to know the values of the shear values of the strains also, because these values are difficult to obtain. So we'll be discussing in this section of strain measurement. So in the strain measurement, usually there are different ways of doing strain measurement, but the most effective and the knowledgeable way is the strain gauge. Measurement by strain gauge. So the strain gauge is a kind of it's a sensor whose resistance varies with the applied force. It's a sensor whose resistance varies with applied force. So as the force is applied, now what do you mean by resistance? The resistance is there in the gauge. The gauge looks like this. It's kind of a rectangular section in which there exists a resistance like this. This is a resistance wire, correct? This is a resistance wire in this form. This is placed in this form because more of the wire will be able to acquire in this smaller space more of the wire. That's why it is curled like this. And these are the two terminal points. It is connected to a Wheatstone bridge. It's connected to a 4-channel Wheatstone bridge. It is connected, and as the potential operates and some kind of deformation is felt behind this, then this resistance is changed. So it's kind of a sensor whose resistance varies with the applied force. As the force is applied, some deformation in the material happens, and this resistance is changed. This change in the resistance is captured by the Wheatstone bridge, and this is further processed. So it is used to measure strain, and what happens basically in this, they are glued to a deformable object. They are glued to a deformable object, and when the load on the object is applied, object expands or contracts or changes its dimension. So strain gauge actually measures this change in the dimension. So there consists of something called as a gauge factor. Gauge factor, and that gauge factor is we call it as GF. This is dependent upon the Wheatstone bridge. I hope everybody of you know about Wheatstone bridge in your 12th class. Everybody have seen change in resistance by strain, or your strain is delta R by R. This is obtained through Wheatstone bridge divided by GF. So strain is obtained by the change in the resistance to original resistance divided by the GF. GF is a factor given by the manufacturer of the strain gauge, and usually varies with 1.5, 1.8, 2.2, something like that. It is being given by the manufacturer. Whenever you buy a strain gauge, the factor comes with it. So you used to find the resistance and change in the resistance given you by the Wheatstone bridge, and you divide it by a particular gauge factor, and a strain is obtained. So now the important point, this is a bit of an experimental things. The important point is how the strains are applied, measured. Let's say I have to measure a strain on this rod. Now this rod is loaded axially. I have measured, and this is a small strain gauge that I have glued over there. So this is applied sigma. The strain that I'll be getting is epsilon xx. If the load applied is sigma xx, I'll be getting epsilon xx. But even if the load is anything else, that means that the strain measured by the gauge, means strain gauge measures only linear strain. If you wanted to measure it in the y direction, you put it like this and apply the load along this, then you will be getting a strain along the y direction. That means the measured strain will only be linear. It cannot be linear, means it will give you a one value of the strain along the particular direction. So if it is like that, then how will we be obtaining the shear strains? How will be obtaining the shear strains? Shear strains are effect of the two surfaces rubbing together. So as a effect of strain, a whole of the body moves. So how will you obtain the shear strain? So there is a technique people used to do by which they used to obtain shear strains, and shear strains are obtained by strain rosettes. So strain rosettes will give you shear strain. Now what are strain rosettes? Strain rosette is nothing but it's a combination of 2 or 3 strains. So they used to put 1 or 2 strains axially and 1 or 2 strain non-axially. So the non-axial strains will give you a shear value because of the transformation. We'll see how this is done. So we'll talk about strain rosettes. Talk about strain rosettes. Strain rosettes. This is a set of strain gauges. Set of strain gauges. So strain rosettes can be applied on the surface and it will give all the normal strains, shear strains, principal strains, all of them. So let's say you have a axis like this. So this is X and this is Y, and you have applied a strain gauge one of the axis, applied a strain gauge in one of the other axis. So this strain gauge will give you epsilon X. This strain gauge will give you epsilon Y. So what I need to do, I need to put one more strain gauge along certain angle. Let's say I have put one more strain gauge along this, like this. Let's say this is 45 degrees. So this strain gauge will give me linear strains, but I have to convert that strain to obtain the shear value. Let's say it gives me E theta, or which is epsilon 45 degrees. So now what we used to do, there is something called as transformation. The matrix that we have, the strain matrix, epsilon ij, that can be transformed, or any of the normal strain can be transformed to any orientation theta. And that orientation, let's say this is now transferred, this is now transformed to some rotation angle theta, and there will be another axis which is epsilon x dash, epsilon y dash. The transformation is like this. So 90 will remain same, this will be x dash, y dash. So at any transformation, the theta by which the transformation happens like this. Epsilon x dash, this can be simply derived, epsilon xx cos square theta plus epsilon yy sine square theta plus 2 epsilon xy by 2 sine theta cos theta. So this is a transformation equation. It's important that you memorize this. This is a very simple linear along the x transformation equation. You only need one for this. So what I used to do, I used to align the strain gauges such that align your strain gauges such that at 0 degree is along x-axis. That means like this, first strain gauge along x-axis 0 degrees, second along 90 degree, that means one along this. So one is placed like this, another is placed like this. So this gives you epsilon xx equals to epsilon 0, epsilon yy will give you epsilon 90. So whatever the value of the strain gauge obtained here, put this in these equations. Then the another strain gauge that we have put in, the orientation is 45 degrees. So you can set whatever the orientation is. Set the orientation to the 45 degree and calculate the value here in this equation. So this will be epsilon 45 degrees will be equal to epsilon xx cos square 45 epsilon yy, sorry, sine square 45 to gamma xy by, now this is what we need to obtain. This will be obtaining sine 45. Remember, gamma xy by 2 is the same component of the strain tensor, gamma xy by 2, that I have explained earlier, cos 45 degrees. So this will give you by 2 plus 90 by 2, sorry, plus gamma xy by 2. So gamma xy will be 2 times epsilon 45 minus epsilon 0 minus epsilon 90. Sorry, so I'm sorry, forgot. I have to look at this also and I have to look at this also. So this becomes an expression for your shear strain. So remember that the strain gauge only gives linear strain. The non-linear or the shear strains can be obtained by putting 3 strain gauges along 0, 90 and 45. You put the values here, you put the values of the strain gauges here, and then you can easily calculate what the shear stress is. So in this way, this gives a complete strain state on a surface. This gives a complete, in this way you can get the shear, you can get the linear strains directly, and then shear strain is obtained like this. So a complete state of stress can be obtained by the help of strain gauges. And in a similar way, the principal strains and principal orientations can also be obtained very easily. So further, I have written the principal strains here. What will be the principal strains? Principal strains can be obtained directly by the equation that we have discussed earlier in case of Mohr circle. So these will be epsilon 1 and 2, the principal values, xx, yy by 2 plus minus square root of, earlier you have seen that it has the stress components, now it has strain components. Here plus tau xy, now what you have to put? Gamma xy by 2, the same component of the shear, gamma xy by 2. Earlier it was tau square only, remember this point. The rest of the points are same. The orientation will be tan to theta and the shear orientation will be minus gamma xy by xx minus yy. Again remember the effect of 2 here. Since it is gamma xy by 2, the 2 has cancelled. All of the things will remain the same. Now we will be doing a very quickly a small numerical problem to make you understand how the rosette things work. Now let's say we have this example that at a particular point the strain rosettes reads like this. Strain along the 0 degree direction is 0.02. Strain along some particular 45 degree directions is this, 90 direction is this. Now I have to find the principal strains and a particular directions. So what should I do? I have told you the way by which we need to find out where is strain rosettes. So you have to, what you have to do? Now we can use directly this equation of epsilon 1, 2. We need to find the principal strains. Epsilon xx, yy and all these things we can directly use. But we have a gamma xy also in this. So what we used to do? We used to use this equation first. But what I said earlier, I said align the strain gauge such that 0 axis is along the x-axis and 90 degree values along the y-axis. If you do this, it becomes very easy to use this expression and obtain the shear value. So that's what we're going to do in this. We'll put the expressions like this and put the strain values like this, and Remember that in this example, intentionally I have taken 45 degrees, but any value could have been given to you. This is 45, it can be 60, 30, any value. Okay, but you will be able to do this like this only, in the same way. So at 45 degrees, you have been given a strain gauge also, and the x-axis value reads 0.02, y-axis reads, because it is along the 90, so this is 0.05, and 45 degrees reads 0.03. So if you put the equation in the gamma xy equation, 2 times epsilon 45 minus epsilon 0 minus epsilon 90, this will give you minus 0.01. So you can obtain the principal values, and this will be 0.053, 0.017. So once you have obtained shear, you can use this equation and use directly this equation, put the value of shear here, obtain epsilon 1, 2. Further, we can obtain the principal directions by using tan to theta value. This will be minus gamma xy by epsilon x minus epsilon y. So this will give me theta value of theta 1 minus 9.2, theta 2 as 80.8. Okay. Now let's say I have to find the shear values also. So the maximum shear will not be like this, it will be gamma max. So this will be epsilon 1 minus epsilon 2 by 2. In the same way, like the stresses were there, we used to put the stress sigma 1 minus sigma 2, the change in the principal stresses. In this, the shear is like this. See, the principal stress tensor and and the strain tensor both operate in a very similar way. It's just the values that they are in different. It's the principal stress represents a different quantity, strain represents a different quantity. But since it's a tensor, all the other operations that we have done will be same will be doing in the same fashion. The orientation theta will be approximately, the case will be 35.8, and theta 4 will be 125. Remember that they will be 190 degree apart. I request you to also make a orientation in which the element has now changed, so that since you have obtained through Morse calculation, you will be able to define the orientations x. So this will be 9.2. Remember, you don't have to put minus sign when you are doing it like this, and the orientation will be now one will be along this, and the another one will be like this. This will be from this to this will be ratio 80.8, and definitely this is 45. Along this 45, the principal value has changed. You can put the other values and do it in a more rigorous way. You know how to do this. So this video has actually become a bit larger. I want to keep it as short as possible. But before we go, since it is a part of strain, I would like you to introduce one very important topic. This needs to be only understood at this elementary level. These are known as compatibility equations. Compatibility equation. What are compatibility equations? Now we know that the strains along the x-axis is du by dx, and along the y-axis is dux actually, and du y by dx or delta x y, and epsilon along the z-axis is del uz by del z. This is all del, partial derivatives, correct? And tau xy del ux by del y plus del uy by del x. So now the displacements are ux, uy and uz, and they are related in the x, they are in the x, y and z directions. So for a 2D dimensional component, the strains are dependent. The strains are dependent on this. I mean that if you wanted to obtain these deformations along the x, y and z directions, you can directly integrate these equations to obtain them. But how will you obtain the shear values? I mean, how will you obtain the strains? You can obtain the displacement by integrating the strain equations. But this will only work when you should also able to differentiate the displacement and be able to obtain this. Then only it's possible. That means it goes like hand in hand together. That means that if there is some kind of a body which is undeformed, I'll not go into the equations. I would like to more tell you about what happens when this is majorly a topic of large deformations or finite strain deformations. So for an undeformed body, when it gets deformed, it's important that it should be deformed in such a way so that all the points of deformation should also be mapped in this. So if the deformation, all the points of the deformation is mapped like this is a deformed, and this is also called as compatible. Compatible means the displacement and strain equations are compatible. If you integrate them, if you differentiate them, you will be getting strains, and if you integrate the strains, you will be getting the displacements. They should be together. That means once you differentiate them, you will be getting the strains, and if the strains are differentiated, then strains are integrated, you should be getting the displacements. So in this way, the compatibility should be maintained. So if the body is deformed, like this is a body and it's deformed, then all the deformed points of the body should be having some corresponding points in the deformed configuration. If such happens, then it's called as a compatibility condition. And if something like that does not happen, then this will be like this. All the points of the deformed body has not been able to transform in the deformed configuration. So this is deformed but is incompatible. If you see books, you will be getting 6 equations. 3, 6, 9 equations in fact. You'll be getting 9 equations of compatibility. These are called as compatibility relations. So additional equations are needed if there is some kind of compatibility difference between the strains and the displacements. If there is some kind of compatibility mismatch between the strains and the displacement, additional equations are required to fulfill that. So these are in terms of equations. In terms of what actually is the compatibility difference in the strains, that means if there is some body and it gets deformed, this is your original coordinate system configuration, and this is your current configuration, and some deformation R is applied on it, then all the deformed points in this body should also be mapped to this. If something like this does not happen, then like this happens. The deformation is trivial. It's somewhere it goes incompatible to the original deformation, and this is what the strain compatibility is. So strain compatibility equations should always be satisfied whenever there is a transfer of strain to the displacement or displacement to the strains. So I need you to get this information in terms of strain also. So I think this is enough for today. We'll be meeting somewhere afterwards in some other video. Thanks for now.